solve these systems, when we're dealing with linear equations, a system of linear equations, one of three things will happen. We will have two lines that intersect in one place, which was the case for the previous four examples. And then the next two examples deal with special cases where we could end up with two equations that give us the exact same line. Here, where we have infinitely many solutions. Or we could have two equations that give us parallel lines that never intersect, in which case we have no solutions. So the key thing with this is understanding what kind of solutions we have. If they intersect in one place, then we have one solution, and it's an ordered pair. It's that point of intersection like we had in the first four examples. But then we could run into some special cases also. So we're going to look at the next two examples, which are examples of these special cases. So we're going to graph each of these lines, and the top one in E is given in standard form, so we're going to find each intercept. The x-intercept, if we cover up that y, we take that out, we have negative x equals 2, so the x-intercept is negative 2. And then the y-intercept, if we take out the x, 2y equals 2, so y is equal to 1. There's the y-intercept, so this line, and again, be very careful following that slope, so we're nice and precise. One comment on the Quizzer test, if you are to graph these, there's the bell, get to class. If we are going to graph these solutions will come out to be integers. When we start solving these algebraically, they will not be integers. May not be integers. They still may, but they may not be integers. But if you're graphing, they will be nice, neat numbers for you. In the second one here, that's in slope-intercept form, so we have slope of 1, or I'm sorry, y-intercept is 0, 1, and the slope of 1 half, so we go up 1 over 2. And what happens is that these two lines are exactly the same. So these lines are intersecting everywhere. We have many, many solutions. This point is a solution, this point is a solution, this point is a solution. So we have infinitely many solutions. So we say that this system is dependent, a dependent system. Now, be very careful. Now, when we solved single equations in the past, and we got something like this, we got x's all real numbers, but not all points are solutions to these two. If they're not on these two lines, for example, this point down here, that's not a solution. So that's why all real numbers is not an acceptable answer to this one. We just say that there are infinitely many solutions as long as the points lie on that line. Now the second one in this case, we have a y-intercept of 2 and a slope of 2. So we're going to be very careful drawing that line, being as precise as we can, following that slope of 2. Okay. Then the second one, we have a y-intercept of negative 1 and the slope of 2 again. So being very careful to follow that slope. We will see that these two lines are parallel and never intersect. So the solutions to these systems are the points where the lines intersect. If these two never intersect, that means we have no solution. And we call this type of system an inconsistent system. And this one we call a dependent system. And the ones we had in the first four examples, where we intersected in one point and we had one unique solution, those were called independent systems. What I want you to get out of this is be able to identify what types of systems would have one solution, what type would have infinitely many solutions, and what type would have no solutions. So these are some special cases that you can run into. Tomorrow's videos, we are going to take a look at solving some of these systems algebraically.